Good afternoon and a warm welcome to everyone who have joined with us today. I am Dr. Shikha with you, scientist from Science Communication and Dissemination Directorate, CSIR headquarters. And at the outset, I would like to congratulate all for the 7th International Day of Women and Girls in Science. In 2015, the United Nations General Assembly established an annual international day to recognize the critical role women and girls play in science and technology. The International Day of Women and Girls in Science is celebrated on 11th February every year since 2016 and aims to promote full and equal access and participation of women and girls in science. Many of us are aware of the CSIR's Jigyasa program as a national level program having sole objective to extend classroom learning and to inculcate scientific temper among school students. The CSIR's Jigyasa program is a unique program for bringing scientists and teachers at one platform and for nurturing young minds. So CSIR through its Jigyasa program today is celebrating this day with a special talk by one of our senior researcher, Dr. Sridevi Jade, who is the head and outstanding scientist of CSIR 4th Paradigm Institute. Welcome you here, ma'am. So I shall take a few minutes to introduce Dr. Sridevi Jade here. Dr. Jade obtained her PhD and Masters in Engineering from the Indian Institute of Science, Bangalore, and joined CSIR CMAX in 1993. And for the past 3 decades, she has been associated with CSIR pursuing R&D and management roles. She is the recipient of National Mineral Geoscience Award for her contribution in the field of disaster management and has also received Sir C.V. Raman Young Scientist Award for her exceptional contribution to earth sciences. Her major activity in the area of global navigation satellite system that we commonly known as call as GNSS based multidisciplinary research has handled several multi-institutional network projects and served on several national and international committees also. Dr. Jade pioneered GPS-based geoscience research in India since 1994 and is an acknowledged researcher in this field. Over the years, she has led several multi-institutional hazard mitigation projects in most difficult terrains such as Ladakh, Northeast, Andamans, spread across the country, which resulted in first-time precise estimates of crystal motion and strain models for Indian plate interiors and boundaries, thus providing recurrence rate of large earthquake in India. She was instrumental in setting up national network of GPS stations as a part of National GPS program of DST and later MOES for monitoring the seismotectonic activity in India for earthquake hazard assessment. Her publications in high impact SCI journal speaks of the quality of research output and the citations indicate the current relevance of her research in the national and international context. She has also led the mega translational project Advanced Research in Engineering and Earth Sciences, covering diverse scientific fields using data-intensive modeling and crowdsourcing approach. So today, Dr. Sridevi Jade will speak on GNSS, GPS and its application in sciences. So students make full use of the talk and enjoy the session. And you may post your queries in the chat boxes below and we shall be taking those questions at the end after the lecture. So with this, I invite Dr. Sridevi for her talk now. Over to you, ma'am.
Yeah. Am I audible?
Yes.
Okay. Thanks, Shika. That's a long introduction. You could have just said 3 lines. I just sent the whole thing because, I didn't have time to cut it. Okay. And good afternoon to all the participants and my best wishes for International Day of Women and Science in Women and Girls in Science. It's a little longer one. So it's my pleasure to be giving this talk. I thought I will talk a very simple talk and also use in between slides some few questions using Mentimeter, which was possible in such a short span of time because of Dr. Somdatta from CCMB. So I would request all the participants to participate in that question answer session so that the session becomes very interactive. And also, that none of you make sure that none of you sleep, whoever is seeing this, or log off. So we can go on for 40-45 minutes and then we can stop midway also. It does not matter. It's just to make everyone understand the science applications of global positioning systems, GPS, which you are aware of. So I will load my PowerPoint with this introduction. I'll share my PowerPoint and then we can go ahead. Share content. Next one. This one. Content only. This share I pressed here, then only this came. No? Share and window. Yeah? For PowerPoint. That the content only.
Windows.
No, I don't want to share the full screen, Shika. I just want to share my PowerPoint. So if I share window, then I will share the full screen. Yeah,
No, in Windows you will see several things coming. So your PowerPoint will be there, ma'am. You just click on Windows.
yeah, I clicked on Windows.
So PowerPoint, is it showing?
Please, or maybe wait, maybe I should open this. It's not showing. The Windows PowerPoint is not showing. So I just share the screen then. Yeah. Microsoft Whiteboard share screen. Okay. Ask them whether it's visible. You can see the PowerPoint.
Yeah, it is visible.
So I'll put it in slideshow mode.
Yes, ma'am.
Now?
Yeah, it has come.
Yeah. Okay, good afternoon. So I'll start my talk for the afternoon. See, all of you, whoever is listening, all of you would have heard of GPS because all of you must be using it in your mobiles for car navigation and all. So basically, I will talk about how do we use it for science and research because today is International Women and Girls in Science. So I thought these applications might be of interest to you. So with that, I am starting. I actually, before I start off, I just have 3 questions on Mentimeter. So all of you have to go to www.mentimeter.com. I'm putting the next slide and give that code number. And then we can start. Okay. Yeah. So all of you go to www.menti.com and use the code 50625153. Then you can answer this first question. It depends on how many participants are there. You can try. Because I can't see how many are there. If they give, it will come here. Na? But they have to give code and all, take time. Yeah. Also, when you answer only the question that appears on the screen, you have to answer. You have to open a separate window on your Google or wherever you want and go to www.menti.com. And then use that code. Then that question you have to answer. Then the response will come to me here online. We don't know how many are there online. Oh, you go to the YouTube, but you need Wi-Fi for that. Huh? I think there's some problem with this. I think, Shika, it's not working. Hello?
Yes, ma'am.
It looks like it's not working. I'll just go ahead with the presentation.
Ma'am, please carry on with the presentation.
I'm not getting any
response is not there. Yeah. So let us start with the presentation. Maybe we'll have this quiz after the presentation.
Okay, then I will skip this menti.com slide and then I will go to the next ones. Okay. because it will take some time.
Yes.
Go to the next slide. Hanging, I think. The presentation is hanging, no? It looks like the presentation is hanging.
Yeah, I am not able to see the next slide. It's still in the first slide only.
That's why I'm not able to see the this thing also. So I'll just escape and share again. Huh?
Okay, ma'am.
Yeah. Actually, we did a trial run. It was working. I don't know. So I'll just escape. Everything is hanging, I think. Other than our teams, it looks like everything is hanging. Yeah, now I will go. Okay, now again I'll share.
Yes, ma'am.
Stop sharing.
Stop sharing.
Share content. Then green. You can see the PowerPoint.
Yeah, ma'am.
We'll just go ahead then.
Yeah, please continue. Slides are changing.
Oh, yeah. So now we skip the Mentimeter slides and we'll come to the, it seems like it's not working. So we'll come to my presentation. So basically what I will talk here is what does GPS do? See, all of you must have used GPS in your mobiles and in your car navigation. So what it basically does is as simple as the figure on your right hand side. Again went off to as simple as the figure on the right hand side. Basically, you imagine your mobile or car is at this point. Okay, and these are the satellites it is looking at 1, 2, 3, 4 satellites. So what does it do is like it determines the position and time of the um, at that point of time wherever you are. So how does it do? I mean, if you go conceptually, because this is a science seminar, you just like for school students and all, you put your compass here and draw a arc. You know, like that, you put a compass, draw a arc where your three arcs meet, that is your point. It is as simple as that. With this distance of the satellite, you have to draw a arc. And then you need one more, because there are 4 satellites, because you need one more for the time. See, like your position is X, Y, Z and time is T. So basically you draw the arcs, you get your position. So it is as simple as that. So what is your position? If your point is Xi, Yi, Zi and your satellites are at Xj, Yj, Zj at any point, because satellites are continuously moving. So at any point, that time, that instantaneous time is what matters, because so that is why this Xj, XYZJ of the satellite is dependent on the time. If you write an equation for a straight line, which most of the children know, it becomes xi of satellite minus x of your point P whole square plus y of satellite minus y of point P whole square. That is your equation. Okay, this equation is basically nothing but the distance between this satellite and this point. And how do you know this is distance? The speed of the satellite signal into the time for the signal it took to come from satellite to the position to this point. So that you know the time taken for the signal to come and the speed of the signal. So in this equation, basically that is what we call as range is speed of the signal into time, which is nothing but this equation. So in this equation, you know the satellite orbits and time. So you know xj, yj, zj. So what you don't know is xi, yi, zi, and your time at this point P. So totally it becomes 4 unknowns. So if you write an equation, you have to write 4 simultaneous equations and then solve for 4 unknowns. So this is the simplest thing which your GPS does. And then how do we use it later on? That's a different aspect altogether. So we just skip the questions and go to the next slide, because I can't change now. So it has to go through the questions only. Okay. So for that to work, you should have somebody who would have put satellites for you to use or look at. So that is called space segment, where the satellites are put, and we should know the position of those satellites, the time of the satellites. That is called the space segment of GPS. And the people who are, and the control segment consists of all the stations or the people who are doing, by putting those satellites up, and then they're monitoring the health of the satellites continuously. That is your control station, control segment. And you are the user segment. Like you use the GPS to get your position, that becomes your user segment. So these are the three segments of GPS. So there are multiple applications, like I've told you, for aviation, for personal navigation, for trains, for so many things. So here, today's talk, we will talk about basically what is the because I have given in my title GNSS/GPS. So GNSS stands for Global Navigation Satellite System, and GPS stands for Global Positioning System. So I will tell what is the difference between those two and how do we apply for science and how complicated it gets once we try applying it to science. So that is what my talk is about. So GNSS is nothing but a global navigation satellite system. So it consists of four satellite global systems which are run by USA, United States of America, and GLONASS by Russians, Galileo by European Union, and Video by China. So all these belong to GNSS, whereas the one which we generally use, GPS, that is what I have given in the first one, Navstar GPS, which is launched by USA. That is majorly used across the world. These are all there, but they are used by specific user applications. Then you have regional navigation system, like in India it is called NAVIC, that is Indian Regional Navigation System. Basically what this, see, the global navigation systems cover the whole globe equally. So they give you the position on the surface of the globe equally. But if you want to improve the accuracy in your region, like for Indian region, we want to improve the accuracy of the position estimate, we use regional satellites. So India has its own regional satellite system which gives coverage for Indian one. Similarly, QZSS is the Japanese one. Then you have also argumentation systems, which are called wide area argumentation system, which most of you must be heard about it, because these are argumentation systems are basically dynamically they give you the best position and the ground infrastructure, everything. This is the term GNSS. So I just thought I will put these slides so that later on, if any participants are interested, they can go through them. But I will not talk in detail about any one of this. So these are the satellite systems. As you can see, this is the orbit. This is the orbit of GPS satellites. They cover the orbital planes and the orbits. This is the GLONASS one, and this is Video, the Chinese one, and this is the Russian one. So these four are global, regional, or space-based navigation systems. So that is this table I put just to highlight how different they are from each other in terms of their orbits, signal structure, reference frame, timing, everything. So when I won't go into details, but if anybody is interested, they can look into it later on in the recorded version. So I just put one slide on our NAVIC, that is our Indian. So it shows how clearly our satellites are put to give the best coverage for the Indian subcontinent. So these satellites are put in both geostationary and geosynchronous orbits, whereas the GPS satellites are at a much lower orbit, that is around 19 and 20,000 kilometers. They are at that orbit, whereas your geostationary, geosynchronous go up to 36,000 kilometers. And all the GPS use CDMA signals that you must be aware of, other than the GLONASS, which uses FDMA. And here in our NAVIC system, we use S-band because it gives very good applications for ionosphere that we'll come to later. So one slide I put on the space-based navigation system, where you get a dynamic positioning on the fly, very precise. You have a geostationary satellite with 36,000 kilometers. Then you have GPS satellites. And then you have your reference stations. So when an aircraft is flying, it gets the signal from the GPS satellites, and also it gets the correction from the control segment. So it gets its that corrections come from the geostationary satellite. So it gets its position on the fly very precisely. So India also has such a system that is called Gagan. You can look into it if anybody is interested, because this slide would be there. So I just put one slide on orbits because this talk is basically Jigyasa talk. So I thought the students may be interested. So you can see the orbital. This is our globe. GPS, Galileo, GLONASS. All the GPS satellites orbits are between 19,000 to 23,000 kilometers. Then you have geostationary, geosynchronous orbits at 36,000 kilometers. Geostationary orbit is basically, when you put a satellite in that orbit, at any point of time, when you look from the Earth, though that is moving, we always see it in the same position. So basically, your Tata Sky satellites, they are all geostationary satellites. So that is why your dish is always focused to one direction, because the satellite is always there for the to look at. Geosynchronous is basically comes to the same point every day in 24 hours once. So that is geosynchronous satellite. Typically, your geostationary is also a geosynchronous, but it stays in the same point at all the time. That is, if you're standing on the Earth and you're looking at that satellite, it is always there. So that is how the definition of geostationary and geosynchronous is. So there are several issues if you have to use all these systems together, because there is interoperability, there is compatibility between all these different systems, because they all use different signals, different reference frame, different timing standards, and different signal structures. So to use this to get a solution on your position is much more complicated. But why? Then you may be asked, why are we having so many global positioning systems? That is because, see, if you use only one, like for example, you use only GPS, then you are dependent upon a specific country. So the specific country can always switch off the signal anytime. Then your dependency, then you'll have to simply shift to the new one. Again, the processing softwares, everything is different. So that is the reason all the countries have their own satellite system, so that they are not dependent on a specific country for satellite system. So that is the advantage. But we are increasing the complexity and also the space junk. So both are the disadvantages of having GNSS. So we just skip the questions. Then we go to, so now I've given a brief glimpse of what GNSS means. So now I only talk about GPS satellites, which we majorly use, all the users in India. Even our regional satellite system, NAVIC, uses this as the reference system and improves accuracy over India using the regional satellites. So this is so I thought we will, and for science applications also, we use GPS, which is launched by United States of America in 1993 for civilian applications. Before that, they were using for military applications. So this is this basically has, this is the orbital plane of the GPS, and these are the L1, L2, L5 are the signals of GPS, and this is the reference frame. So now I will tell you how do we use it to get the position for science applications basically. So this is the control segment of GPS. So this is the signal. So when I said L1, L2 in the earlier slide, this is your L1 and this is your L2. This is the phase carrier signal, carrier. Then you have a code. This code is modulated over this carrier L2 and L1. So you have P code, which is a very precise code which is used for military purposes. Then you have a C by A code, which is a coarse acquisition code. And in your signal, other than L1, L2 carriers, these carriers should get modulated with these codes and also navigation system data, that is the orbit and time of from the GPS satellites. So this is your signal structure. So now coming to positioning services, like I said in the earlier slide, if you're using P-band, then you get P code, you get precise positioning service. This is not available for civilian use. This is only for military and authorized users. So what we use even for science is what is available for civil users. That is standard positioning system. That is, we use the phase of the signal, not the code of the signal. So this is how the positioning works. What you all see in your car navigation and mobile is this positioning. That is, you look like this is your mobile, you think XYZ is the position of your mobile and the time in your mobile. They directly look at the satellites and get the position. So this position is usually off by 50 meters. See, when you say horizontal, that is your lat and long. When you say vertical, it is the height. So the lat and long, it is off by around up to 50 meters, and in the height, it is off by up to 100 meters. Whereas in your mobile, what happens is, since your mobile is looking at the GPS satellites, and then it also gets signal from your mobile towers, they keep correcting it. So the accuracy which you get in your mobiles is slightly better than what you get on in your car, basically. Or if you get it, if your car GPS is linked to Wi-Fi, then here also position you will get better. But still you're off. Like, when you go in a car, it says you have reached your destination, but sometimes your destination is off by 50 meters. And when you're trekking on mountains and all, your height will be off by 100 meters. So this is point positioning. And then you have differential positioning, which we use for aircrafts, where basically they have a base station where they have a reference station for which you very precisely, with an accuracy of less than centimeter, they know the position of the base station. And then they have a remote station which is looking. So both these stations are looking at the same satellites at the same point of time. So the common mode errors between this looking at these satellites are same at both the stations. So that error it captures, and then it keeps correcting itself and then giving those signals to your aircraft. So this position is up to meters. You get accuracy, horizontal accuracy, that is in lat and long, up to meters. And in height also, it's up to 10 meters. So this is what they call, what you hear, a common word, many of you would have heard, DGPS. So this applications is this position. Because the DGPS positioning works only for a distance of about in the radius of 300 kilometers. Because the common mode errors the signal passes through are same only in the radius of 300 kilometers. Beyond that, it does not work efficiently. Whereas this positioning works for any, like between a station A and B, the distance can be 3000 kilometers also. You still get accuracies up to centimeters. So what we do here is we process the baseline vector. How we do it, I will show you later. So this is how we use it for science. Basically, we have two stations with two GPS receivers A and B, which look at GPS satellites, and they solve for the distance between A and B, which is called the baseline vector. Okay, and then they get the position, like at any point of time, like that instantaneous time. So over a period of time, like you have a position today, and then over a period of time, like after a year, you have a position. So what you get is the velocity. So even we are all moving, like, I have shown these tectonic plates. All of you must have studied in your school. Each of these tectonic plates have a velocity associated with them. Like you can see, these arrows are the velocity of the tectonic plates. So GPS basically picks up all these velocities. Earlier, before the advent of GPS, we did not have precise velocities of the tectonic plates. Whereas now we have very precise velocities of all the tectonic plates, which improved very much the research part, because earlier we didn't have this kind of precise positioning. The only thing is one should remember is GPS will give you position only on the surface of the earth. It does not give you below the earth. So like if you want to use it for a mining application and all, it does not work. But there are ways to do it, but right now, as far as we are concerned, whatever GPS we use is to pick up the surface motion. That is basically, even in the surface motion, your latitude and longitude, it gives very precise, whereas your height changes it is not that precise. That I will tell you why is it so as we go ahead. So this is what we use for science applications. So we just keep the Mentimeter questions because that's not working. So we'll go to many people are asking Shika questions on what I'm using, why they are not getting Mentimeter. I can see the questions coming on the Mentimeter slide. Very many people are asking. I don't know. What we thought is after the talk is over, maybe you can take that quiz. We will see then.
We'll take the quiz after the talk is over.
Okay. Anyway, you have the questions and the code. So on the Mentimeter site, you should be able to answer them. So I just put the kind of receivers which we use for science applications are different. They are called geodetic grade receivers. So these receivers have so many channels, and at any point of time, they can track as many satellites as they are visible above that point on the surface of the Earth. So you can see one of the plot which we have plotted for that particular instantaneous time for our station, which is in Udupi near Mangalore. That is in state of Karnataka. We are located in Bangalore. So it shows the plot of how many satellites it is tracking at any instantaneous time. So you can see it is tracking GPS, GLONASS, Galileo, even the Japanese and video satellites. So we have this kind of receivers. And if you see, this is how a satellite plot looks day and night. Like when we are on tracking from our Udupi station, this is how it looks. So the one which you see, those are all faraway satellites. The one and all satellites are tracked at any point of time. So now, before I tell you how do we do the position for science applications, that is the main thing of this talk is how do we use GPS positions for science applications. I have to give you a little bit of some definitions like what is the reference frame we used. See, like I had told you earlier, the satellites are in a celestial reference frame. This is a completely different reference frame. And your receiver is in terrestrial reference frame. And the terrestrial reference frame is defined as Earth-centered, Earth-fixed. That is, your origin is in the center of the Earth. That is inside the Earth, 0, 0, 0. So, and from there, you have Cartesian coordinate system, X, Y, and Z. So this is the reference frame we use for our position. And whereas your satellites have a celestial reference frame. So we calculate XYZ of the receiver in Cartesian coordinate system and then transform it into geodetic latitude, longitude, and height. That is how this works. And then when it comes to height, see, this is what which I use. I see many students, everybody thinks that they get the height on the GPS is at the actual height. So it is not the actual height because, you know, what GPS gives you is an ellipsoidal height. That is, if you represent the surface of the Earth with a mathematical ellipsoid, that height it gives you. Whereas your surface of the Earth has so many undulations, that is called geoid. So that is what is your mean sea level height. So if you want to get the height using GPS, there should be a correction from ellipsoid to geoid. Some of the GPS applications automatically correct that, but some do not. So that is how the heights in some mobiles you get correct, and some mobiles like you get wrong height. And I saw once on a trekking thing, people were arguing with each other. No, my mobile is showing this, yours is showing that. So that is the basic science difference. And also, you know, when they do this land surveys and all, you know, they're using GPS, the maps and all. They say the stormwater drain is here, but then when you go to that location, the stormwater drain is not there. That is because they are off by that many meters. So that is also many people don't realize. I keep reading in the newspapers also. So how do we do? We solve, like I've showed you, we solve a baseline vector. So in the baseline vector, you have 2 points, A and B. So you need a very precise reference point A to be able to solve the point B. So for that, there is a international GNSS service, which is purely basically which runs this network of stations, and all the station data is available for any user free of cost, public domain. So this is the network. And these are the stations which we have, so many of these. So like if we are doing positioning in our Indian continent, then we use all these stations which are closed hereby as our reference stations. So like you see, I put a star. This is the reference station which we operate. See, actually when GPS became fully operational, that was in 1994. That is when we established this station for civil users. So this is in Bangalore. So this is the station we have in Bangalore. That time I was studying at IISc Bangalore. So that was me at IISc Bangalore. I was doing my PhD, and that is when we set up this station. So we started long back as soon as GPS became operational. So this is the station. So now coming to the position, we'll go to our first slide. I repeated here. So I have told all of you how do we do by drawing a compass. Now we'll come to the mathematics of it. Okay. So here we have, you call this as a range, which is nothing but c into speed of the signal, which is c, and the time taken for signal from here to here, which is equal to this. So that is the simplest solution. And you put 4 simultaneous equations and then solve for it. But then in reality, this is not that simple, because first of all, this range which you are getting, the satellite signal itself is not the actual range. The R is not the actual, it is pseudo range. That is because when this, for the simple reason, this satellite clock is atomic clock, whereas in your receiver we don't have atomic clock. So there itself you have clock errors related between. So the time t which you are giving is not the actual time, because you know the difference of the time of atomic clock and the clock in your signal also you have to add to it. Similarly, there will be errors in the orbit. The orbits are also not precise. Everything is relative. And then when the signal passes, it passes through our atmosphere. So as you all know, any signal that goes through atmosphere suffers refraction. So that also we have to account for it. Then you come to receiver. We cannot have receiver hardware as good as satellite hardware. Then your receivers will be very expensive. So you have normal geodetic grade receiver, which has its own noise, its own errors and all that. So the actual range is, the measured range is actually not it doesn't represent the actual value. It is called pseudo range. That is what we call it, because it gets affected by all these things. And then your signals, as I've showed you, how do we measure? See, when I told you in this slide, it is not as simple as, you know, from there you get a signal, you track it here, and then you do it. It is not like that. The signal is basically has both P code and a phase. So the satellite generates the same code, and the receiver also generates the same code. So when both the codes meet, full correlation like this has to come. Then only it gets logged. And that is what we use for when we use code. That is what we use for positioning. So when you say the satellite signal received your reach the receiver, it should be in this full correlation. That is when we say it is reached the receiver. So, but we can see the code is not, we can't use because this is not available for civil users. So it is available only for the precise code is available only for military. But we use course acquisition code, plus we use the phase of the signal. So any signal phase is like this. So from your satellite, one signal comes. From your receiver, one signal comes. So when this satellite signal reaches the receiver signal, what is the phase difference between the satellite and the receiver is what we solve for. The phase difference, that is that is the difference between this, like when it gets locked, what is the difference in the phase. So this is what we solve for. So that we do not actually, you know, so that solving for that observed phase difference, it becomes very complicated, because how many phases it has passed before you locked, we do not know. So that again, it becomes one more unknown added to your equation. So I am just trying to simplify it so that the conceptually it is understood, even if it is not understood mathematically. That is the whole idea here. So I am not putting much equations because then it becomes very complicated. So this is the map which I am talking about. So you start from here. So you have orbit error, clock error. Then sometimes, earlier they used to deter. See, they want anytime any country who's operating that satellite can deter the signal. Like if there is a war, they will deter the signal. Then we won't get the correct one. So that also we have to take into account. Then when it passes through the atmosphere, you have refraction due to ionosphere. Ionosphere basically is between 70 to 1100 kilometers or something. I don't remember the correct thing. So that is ionosphere. Then you have troposphere, 0 to 70 kilometers. So both refraction it suffers, and then comes to the antenna. This is where your signal gets locked, which is then transmitted to the receiver. So when the signal, when it comes to antenna, there is some bird flying and all, then it will reflect and come. So that is called multipath. So we have to solve for all these errors in the equations before you get the position for science applications. And also I want to state here, the sampling interval, like for GPS satellites, when we put a receiver, the sampling interval, we collect data every second and every 30 seconds. So for it, like we will, for example, say we will stick to the sampling interval of 30 seconds. So at that 30-second instantaneous time, you will have like the equation which I have shown you earlier. This equation, you will have at any instantaneous for each satellite every 30 seconds one equation like this, and for all the satellites your receiver is looking, you will have. So you will have multiple equations. So it is basically an overdetermined system which you put it in a matrix form and solve using parameter estimation, least square and techniques like that. So it becomes, and that too you solve it for every 30 seconds. So like for me, I want to get a position, daily position, then I process the whole day's data with a 30-second interval before I get the daily position. So here I've simply given simple equations. This is in the idealistic world where you have speed of the signal into t is equal to this equation down and you simply solve. But that is not the case. Then you have what I talked about, pseudo range, where you have all the errors I clubbed into one. So we have to solve for all the errors. So for example, you have, like you said, A is your reference station, B is your station for which you're solving for the position. So when this station, the receiver at this station looks at the same satellite at the same time, both the stations, like this A and B look at the same satellite at the same time, then you can estimate the slight error coming because of the satellite clock. So we can minus that. Similarly, if you have two stations looking at two satellites, the receiver clock gets cancelled. Like that, we reduce the errors, and then we keep on reducing the errors till we get the best solution. So when you write this equation for code signal locking, you have this. This is your distance rho, and this is your range, pseudo range, and this is your error term. I simplified it. Otherwise, you have so many error terms. Similarly, in phase pseudo ranges, you have one extra one because we do not know at the point of locking the phase difference how many phases have passed. So that we have n. So this becomes an overdetermined matrix system which you need numerical methods to solve, and we solve for it. So this is when we started in the beginning with a simple compass and drawing the R, it becomes so complicated. Conceptually, I am telling you, in the equation wise, it becomes much more complicated. Then once we do this, we get the precise position. And we cannot do it instantaneously because we do not have the precise orbits of satellites instantaneously. In the signal, whatever orbit of the satellite comes, that orbit is off by that many meters. So we have to wait for that control segment analysis centers to post the precise orbits of all the GPS satellites, which typically they take 2 weeks to post. Then we use those orbits and then we solve for science applications. So that is how it is done. So these are called the GPS observables. We solve for these observables to get the position at that time. Okay. So I think we will skip this. Okay, we come to the science applications now. Simplest form. So you have a GPS network of stations. I think I put the network of stations. No, I didn't. GPS network of stations if you have, GPS data, let us say. Then if you want to see the major science applications which we use in our institute is what I am talking about. There are much more than this. So basically we use it to find out what is the velocity. Like I say, Bangalore is moving at a rate of 5.5 centimeters per year and Himalayas is moving at a rate of around 2 centimeters per year. So those kind of things we get. How do we get? I will show you. And then we use that velocity to study earthquake hazards. That also I will tell you how we do. And you can also use that to study landslide, glacial and volcano, which we do not do. But this is also one of the areas we basically use for earthquake hazard studies, and we also use for atmospheric studies, like when the signal passes through troposphere, ionosphere, it suffers like in troposphere, it suffers a delay. Whereas in ionosphere, it suffers both delay and advance. That is because ionosphere is a dispersive medium, whereas troposphere is a non-dispersive medium. So from that delay, the signal suffers, we'll capture that delay and then we can calculate what is the water vapor content in the atmosphere and what is the total electron content, that is the ionosphere content in the ionosphere. Then we can use this for ionosphere studies and this we can use for troposphere studies and also for rainfall. So we do water vapor, ionosphere and seismic studies in our organization. This is this thing. So I'll just show a glimpse of, under 5 slides are there, I think, glimpse of our studies. How do we apply for science? So as you all know, this is the seismicity map of India. This is like you can see all these are events, and when you see it, automatically the events trace our tectonic boundary because you have the maximum events there because our Indian plate is subducting below the Eurasian plate at a depth of around 50 kilometers below in Himalayas. That is called main Himalayan thrust. At a rate of around 60 millimeters per year approximately. It varies from I think 12 to 16, 17 millimeters per year is the rate at which the Indian plate is going below the Eurasian plate along the main Himalayan thrust, which is at a depth of around 15 kilometers, 15 to 20 kilometers below the surface. So this is the seismicity map of India. So we get so many earthquakes. Wherever you see these beach balls, they are called the focal mechanism of the earthquake. So these are the major earthquakes. So the remaining all, we just put dots, that is the minor earthquakes. So this is this thing. I don't know how many of you know, we had a major earthquake in 2004, which caused a tsunami, which came and hit the Chennai coast, and there was huge loss. And similarly, in 2001, we had an earthquake, which happened in the Gujarat region. So what is the difference between these earthquakes is, this is a tectonic boundary earthquake, whereas this is within the plate. There is no boundary here. So the movement happened along a fault. So that is intraplate, and this is along the boundary of the plate. So these are the two earthquakes, 2004 and 2001, which caused huge loss of life and property for our country. So how do? We basically establish stations like this. This is our continuous station. So continuous station means it works 24 hours a day, 365 days a year, continuously for so many years. Like our Bangalore station, we set up in 1994. From then till now, we have data at every 1 second and 30 seconds. So similarly, this is a station in Ladakh, Himalaya. This is called Hanle. Most of you would have heard of our observatory, the astronomical observatory, where recently it has come in the newspapers that they have put a very huge telescope and all that. So this is there. This station was set up in 1997 at Hanley. So it is working from then till now. So this is the antenna. And then we put our receiver in a small box. This is the receiver. And this is one of the stations in Kashmir, which was set up in 2014. So you can see the antenna and this is the receiver. So these are permanent stations which run throughout the year. And this is one of the pictures of Ladakh Himalaya. We put this picture because of the next Mentimeter question, but then we are not doing. So for this, we put that picture. Ladakh Himalaya is located in where for that? These are the campaign mode surveys where we go every year 3-4 days and occupy a particular point, come back and again go and occupy after a gap of 6 months or a year. So this is one of the stations in Andamans. This is in Himalayas. So these are the campaign mode stations. So now I will come to our observation network. If you can see in this map, all these triangles which you can see, these are all our continuous stations. And all that small circles you can see, these are all our campaign stations. And you see the arrows, this is how the Indian plate is moving. And all these small, the blue things are all the earthquakes which we minimized so that, you can see our points clearly. So this is our network which we use. So some are established 94, some in 97, some in 2001, and some in 2014, like that. Recently, we established one station in Ladakh Himalaya just 4 months back. So all the whatever station, all this data we collect. And then we process it using, but it's not a software, it's a public domain thing which we have to basically write shell scripts to use for our Indian subcontinent to get the positions. So this is what we do. And I will show you. So you get once you solve for a day, we see every 30-second data we solve. So you get a position every 30 seconds. So I have only plotted here. This is 1 day's position. This point is, and this is the error bar of that position, daily position. In spite of removing all the errors also, we are still left with some residual error. So for each day you get a position. Okay, and then if you measure like a week in 1 year and then 1998, and then you go and measure the same point for a week in 2000, then you can plot the positions come like this. So this cluster is when you expand it, it will look like this. So this is the class. So if you measure like this over a period of how many years, this is 1998 to 2008, 10 years. Then you draw a line, straight line, that is your velocity. The slope of this line is your velocity. That is how much you are moving in the direction north. This is a station in Sikkim. And this is basically how much you are moving in east. And this is how much that particular station is moving in height. But height, you have errors are huge. So this is when we make measurements once in a way. So when you have a station like IISc for so many years, then we have actually here the one I put is less, but we have the similar, these we call time series for that many from 1994 till date. And this is the position of the station using continuous data. So this is the Hanley station for which I showed you the photograph. So these are all using 30-second sampling interval. We solve for each day's position and then we get so once you plot all the position, you get the velocity. So that is how you achieve less than 1 centimeter accuracy for science applications. So what do we do with this basically? So once we get the velocity, we plot at all the stations, like you can see all these arrows of all continuous data. We plot, these are your arrows. So like you see Bangalore is moving at this rate, whereas Himalayas is moving at this rate, around 20 to 30, like that we show. So this is, so when you see I put this box, so Indian plate is basically moving like this in a clockwise direction. when compared to the surrounding plates. These are all, see, you can see a clockwise motion when you combine all these arrows and see. So this is in the global reference frame, that is your ITRF. But if you want what is happening within India, you you have two cars going. Okay, one is going at a higher speed, other. So you need to get the relative speed to know what is happening, your relative motion. So here also it is similar like that. So this is the velocity of the tectonic plates, but we have to find out, subtract the velocity of the Indian tectonic plate to get what is happening within India, that is the regional motion or the relative motion. So for this to know, you first have to find out what is the pole of rotation of the Indian tectonic plate. So that we estimated using all this. See, for that you need at least 20 years of data to get a precise estimate. So all this we estimate using 20 years of data, and you can see this is the pole of rotation. Like you can see ITRF different reference frame. So at this point, from this point, there will be a rotation with which this rotates. The Indian plate rotates. Like you have to visualize that in 3 dimensions. So we found out that, and then we subtract that motion from the Indian plate motion to get what is happening within the plate. So this is how it is, as you can see the vectors. So when you subtract that motion, now you don't see any vectors in this part of India, which is called rigid Indian plate, because there is hardly any motion here, which you can't see any vectors. Whereas along Himalayas, you can see lot of vectors moving southwest. So that is the relative motion of Himalayas with respect to the rigid Indian plate. So this is where you have the plate boundary. This is the relative motion of this Himalayas, all this and Andamans with respect to yours. So once you get the relative motion, so how do we use this? This is what we call India fixed velocities. Like for example, like I said, we had a 2004 earthquake. Okay, so if you have made measurements before the earthquake and after the earthquake, we can capture the motion of that particular point during the earthquake. Similarly, if there is no earthquake, like for in this region, Himalayan region, if there are no earthquakes, we know the motion of this Himalayan region with respect to rigid Indian plate, then we can model. See, this motion is on the surface. So what is that is happening below the surface? For this motion to be captured on the surface. So we can do inverse modeling using mathematics and all, and then we model that. So these are the major applications which we do. So I will show you two simple applications. Like for Andaman, this is Andaman Earthquake. So when Andaman Earthquake happened, our stations captured, like during the earthquake, Car Nicobar moved around 6 meters. Port Blair moved around, if I remember, I think around I think around 5, I think. You can see these vectors. Yeah. So they all move so much. This is the motion during the earthquake. And even the stations very far from Andamans like IISC, Chennai station, they all also moved during this earthquake. It shook this whole region completely because it was a mega earthquake. And here we also caught the difference in the height. So there was an uplift in the, because here, there was an uplift, like, Andaman Island had an uplift, whereas Nicobar had a subsidence. I don't remember the numbers, but you can refer, these are all published. Here we could catch even the difference in the height because the signal is so high and the error is so less. So we could easily capture that motion. So then using that motion, we model what is that, how the earthquake has ruptured this portion that caused this surface motion and at what depth did it rupture. So we can get a model of the earthquake rupture zone from this surface velocity. So we know that the rupture zone is this length, this width, and at this depth, and it moved by this much instantaneously to would have caused that huge earthquake. So this is one of the science applications. Similarly, for Himalayas, only two science applications I am giving. For Himalayas, we have done. I traveled myself from 1997 from Ladakh, Himalaya to Arunachal Himalaya, full Himalayas. This is not ours, Nepal. And from 2000, I think 14, we started Kashmir. As you can see, this is the Kashmir Himalaya. So how do we use this? We use this surface motion vectors to find out what is the subsurface motion that is happening to be able to give this deformation on the surface. So as we all know, in Himalayas, there is something called main Himalayan thrust, which subducts below the Eurasian plate. So we get the motion, what is the slip on that thrust that gave motion. So that we model. So this is one of the applications. And we can also, use the same things to calculate, like now you know what is the motion, then you calculate the strain. So you know how much is the strain accumulation on the surface. And when was the last earthquake that occurred? Like in Kashmir, what was the last earthquake? So that earthquake released this much of energy. And now for past so many years, this much of strain accumulation happened. So then we can give a measure when exactly not when, but what is the recurrence interval of the earthquake and what is the magnitude. So recently we have given that for both Kashmir and Garhwal and Kumaon in Himalaya. I just gave the publication. If any students are there, they can refer to it if they're interested. So that also we have given. So I think under 2 slides are there, atmosphere and ionosphere applications. That's for GPS remote sensing. So see, your water vapor, when the signal passes through troposphere, it suffers delay. And that delay, 90% of the delay is because of the hydrostatic delay. Only 10% is because of the water vapor. So that 10% delay, we separate it out and then we calculate how much is the water vapor that caused this delay. We calculate it for every 30 seconds. Then we calculate it for the every 30-second interval for that many years. And if you see these bars are those that are calculated water vapor column over that period of years, so many years, 10 years, 20 years at this station. So you can see very clearly which are the moist ones, which are the desert areas by seeing the water vapor. Like Ladakh, you hardly get any rain, so desert area. So similarly, this is the most precise measurement of water vapor. So you can compare, you can correct whatever water vapor you get from satellite data using these studies, and you can also incorporate it in weather forecasting, which they do as a routine thing abroad. In India, we are not yet doing it. We can also use it to capture cloudburst and all, because your water vapor is correlated with rainfall. So if you see, this is the rainfall from satellite at Hanle station. That is the desert environment where you don't have much rainfall. So it's a very low rainfall. Even that is caught by our water vapor. So this is the water vapor measurements every 30 seconds. And this is the rainfall pattern which is being caught. And then we also, I don't know how many of you are aware of the cloudburst in Ladakh in 2006. So we could capture that also using our measurements. So this is one of the applications in science. And then we have the last slide where we have the ionosphere application. So ionosphere, when it passes, this becomes much more complicated because you have for each satellite 30-second data, you get, like you can see, for a day, like you're calculating 0 to 24 hours. For each satellite, you get ionosphere for 30 seconds for each satellite. And then you have to average it out to get for a day the ionosphere data. That is called total electron content. So this is much more complicated. And then we plot it. So if you go to, this is my last slide. So this is the stations for which we plotted the ionosphere. This is basically, you have an ionosphere model. So we calculated ionosphere using our GPS data, and these are basically the bias between the model and the observed data. So we can improve the ionospheric variability studies over Indian subcontinent using this kind of result. And on the right hand side, you can see this is your GPS tech is what we got from our observation, and this is from the model, and you can see the correlation and how it depends on the solar activity, because solar activity is the main thing, variable in your ionosphere content. So we plotted and showed how much it correlates with your sunspot number, solar flares, etc. So this is under basically for ionosphere variability studies. But nowadays they are also using this as earthquake precursor studies, because before an earthquake occurs, there is a disturbance in the ionosphere which can be used. This is for short-term precursor studies, like Japanese and all. They do it for short-term, like for the 2011 earthquake, they could come out with 3 minute before they knew the earthquake is occurring. But then 3 minutes is too less to evacuate people or anything. But still, it is a progress in science. Anything little, even a minimum increment is a progress in science. So this is the other one. This is the last slide, and then we can take questions. In this slide, I put what our institute. See, we are a fourth paradigm institute. Basically, that is data intensive scientific discovery. Basically, you all must be knowing. I think even school children know big data, they keep talking. So we do research in big data science. So that is what is called fourth paradigm of science. Your three paradigms are basically your experimental science, where you do experiments, then you solve those experiments using equations. That becomes your second paradigm. Then advent of computers, you solve those equations using computers. That is your third paradigm. So we are the fourth paradigm institute. So we do research in the big data science basically. So with this, I end my presentation. I'm so sorry that we could not do that Mentimeter thing. We tried, but I don't know what is the issue. So it's okay. So I can take some questions.
Okay, thank you so much, ma'am. So, do you want to have a Mentimeter session now, ma'am?
Yeah, you can.
Actually, if from your end it will be done, it will be helpful, ma'am. I don't have that presentation.
Same presentation only it is. I put the Mentimeter slide. You want me to go to the Mentimeter presentation?
Is it there separately? Then we can have it once, or otherwise we'll take your questions as you suggest.
It is open na here. But we are not able to take in this slide, no? In my this PPT, it is not working, no?
At that time it was not working. If we can try once again.
Okay, we'll try from first question. I'll go back. Now it is moving very fast.
Yeah.
Initially, there was some problem. So we can take quickly. It will be nice. Okay, we are almost there, na? Yeah, we started from this is the first question.
Okay.
Select the class you're studying, because I thought I will know the profile of the participants.
So I think the participants, they have to go to menti.com. menti.com and use a particular code 50625153.
But you don't have Wi-Fi, no? Okay. It's not working. It's okay, then we will leave it.
Yeah, yeah. Yeah, we will move ahead, ma'am. We will move ahead. We have few questions. So first of all, I'll thank you for this extremely informative talk. So we saw how scientifically this GPS and GNSS can be used for studies related to natural hazards. So like earthquake hazards. So I'm very sure the talk could have helped many students who are connected with us to understand the concept of GNSS and GPS which was explained very beautifully here, and how these are used for scientific applications. So thank you, ma'am. Once again, we'll take the questions.
Yeah,
The
I
first
stopped
question.
sharing my slide.
Yes, ma'am.
Yeah.
We have our viewer Atul Dev. So the question is, how more accurate PPS is as compared to GPS?
The PPS actually, is very simple because you use code there. So See, the difference is if you want an instantaneous position, your GPS is off. Like even if I have to get a precise position 1 centimeter, that is in post-processing mode. That is up 15 days after you measure. But if you want instantaneous position, I think the difference will be in meters, because you get around meters of accuracy using uh, 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 phase data, whereas in code data you get centimeters.
Okay. We have another question from Dr. Shankara Gomati S. What software or simulator methodology is best suited exactly to implement these parameters of QoS?
QoS?
QoS results.
I don't know what is QoS. I'm not aware of it. I don't know.
Okay. So maybe there is another comment from Dr. Shankara Gomati only. Ionosphere speed may be greater than 98 kilometer and go up to 500 kilometer. So you have any comment on this, ma'am?
No,
Okay.
but the
So
question is not clear.
clear, yeah, okay. So maybe Dr. Shankara, if you want more clarity, you can post it again.
Or I gave my email ID in the last slide, she can send it.
Yeah, you can communicate with ma'am over email. So, ma'am, how big is this data that we call about big data? So you just show some light on that.
See,
And
actually, yeah.
this GPS and GNSS processing. So, how is the amount or quantity of data that you process? How big is it?
See, here I want to make a comment. GPS application to science is still in third paradigm. We have not gone to the fourth paradigm. That is, see, the difference between third paradigm also has huge data sets, even in climate, whether it is GPS and all. Whereas when you use the data and mine it and use it for a discovery, then it becomes a fourth paradigm. So right now we are still in the third paradigm. See, it's huge in terms of a single day's data of a particular station. If you take 1 second interval, will run to, I can't recollect actually. It's quite huge. And then you have for like when you're doing ionosphere applications, we solve it for each satellite. So that is also quite huge.
Yeah.
But I can't remember in terms of bytes how big it is. That would be hard.
And depends on the frequency that you require also. You can,
Yeah, if your 1 second data is very huge, 30 second is
right,
manageable.
right. Okay. So we have a young guy connected here, Atul Dev. He is saying he is in standard 11.
Mm.
And if I want to study further in this field, what course should I take? Atul.
That's a very interesting question, Atul. You know, some very recently they started teaching this GPS as a subject. But I think if I remember in IIT Kanpur under civil engineering they do, and in IIT Mumbai under earth sciences division. But I'm not sure about normal institutes where they teach this kind of this thing. Like I was asked to teach in IISc, but then I didn't take the plunge. I didn't shift from CSIR. So
And these are, I think, specialized courses.
specialized.
Specialized. So it will be mostly in masters. In bachelor's, it will
No, they teach actually, GPS in IIT Kanpur, part of civil engineering, they teach.
bachelor's course. B. Oh, that's great.
But in IIT Mumbai, they teach in masters.
Masters. Yeah.
Couple of couple of lectures initially when they started the course, I went there and took. That's why I know as a guest faculty. After that, now they only do.
Okay, ma'am. So I think we have only this comments. We'll move forward. So thank you very much, ma'am, for sparing your precious time with us. And thank you, the entire team at CSIR headquarters and also the entire CSIR Jigyasa team for the webinar, and special thanks to all the students and the audience who are connected with us today. So let us keep celebrating many such days, recognizing the contribution of each and every woman and girl in science in the nation and across the world also. So take care of your health and be safe. Goodbye for now. Namaskar.
Thank you.
Okay. Thank you, ma'am.